Quick show of hands just to get started. I've got a few questions. How many of you have ever had a user come to you and wish that their software was slower? Okay, cool. Nobody. Good. Users always want things to be faster, don't they? They always want things to be snappier, be more responsive. And when you consider that a lot of the software we build has a direct impact on people's productivity, people's job satisfaction, software needs to be fast, doesn't it? It needs to be performant. Okay, next question. How many of you have ever had a user come and wish that the software that you built for them was less safe? That they would fill a really long form in the software, they'd submit it, and then all that data would just disappear? Or a slightly different question, how many of you wish that you got paged more often? You wish that your software went wrong more often? No, okay, that's like what I expected so far, it's good. I'm sure you've all been there where you've had something you've built go wrong because of something that was completely out of your control. A server upgrade goes wrong, a Kubernetes cluster gets upgraded incorrectly, and everything just breaks. And it's not your fault, and your page goes off, and then you're sad. And the last question, how many of you have ever had leadership in your organization, someone senior come to you and say, I wish the software we built cost more money, or it used more resources, it was more impactful to the environment? Nope, still no hands. This is going just as I expected, because we want things to be sustainable, don't we? And I believe, actually, we have a responsibility as people working in software to make the things we build as sustainable and as environmentally friendly and, of course, cost-effective as possible. These three things are three very different requirements, though, aren't they? And as the great Oprah Winfrey said, you can have it all, you just can't have it all at once. These three different requirements bring up three very different requirements, don't they? Three very contrasting things. How do you make something safe and performant, but also sustainable? How do you have all of these three things? And that's what you're going to learn about in this talk. Not only that serverless technologies are the perfect place to get started with Rust in production, but also how that combination of Rust and serverless allows you to build software that is both fast, safe, and sustainable. I'm James Easton. I'm currently talking about all things serverless and event-driven architecture at Datadog. I'm a Microsoft MVP, and later I'm going to be joined by Luciano Mamino, who's a really good friend. It's actually the first time we've shared a stage, which is actually kind of cool. Woo woo. And to start, I want you all to forget everything you know about your day jobs. Forget your Jira backlog, forget your pagers, forget everything you do in your day job, forget all of that, because you're all now developers for a completely fictional pizza delivery company called Plant-Based Pizza. And this is you. You go into work every day, you've got that perfect balance in your job where things are just about complex enough to be interesting, but you kind of know what you're doing. You feel like you know what you're doing. You feel like you can deliver quality work. And this is Helen. Helen's a principal engineer at Plant-Based Pizza. She's also your direct line manager. And she comes to you with a new requirement, a new thing that you need to build. You need to build a new loyalty point service inside Plant-Based Pizza. Not only that, she gives you some constraints that you need to work within. You're going to be the only person working on the project. There's only you. You can't rely on any other internal platform teams, any infrastructure teams. There's just you. The thing you build also needs to be performant. It's not on the critical path of the application. It's not something that's going to affect people placing orders, but you still want it to be performant. You don't want it to affect that wider user experience. And of course, the company, being Plant-Based Pizza, has very ambitious cost and sustainability goals as well. Oh, and the last thing she says, actually, just as she's leaving the room, she says, you need to deliver that in a week. You've all been there, haven't we? You feel that fear come over you, and I'm sure when you've been there in that situation, you've tried to say something about trade-offs. You've kind of said, you can't have all them three things. You can't have speed, safety, and sustainability. It's impossible. No movement. She says you've got to carry on. So then you bring out the big guns. Say it depends. Nope, still no movement. You need to go off and build it. So you think this could be an interesting challenge. You've started getting into Rust, you've started building things with Rust, you've got complete control over this project, so maybe this is actually a good place to get started. And this is the existing system that you need to work with. So there's another service that's publishing things onto a Kafka topic, these order completed events. You need to pick up that order completed event, you need to use that to increment the loyalty points that a user has. And then you also need to build some kind of web-facing system so people can retrieve the loyalty points that they have. And you decide this is roughly at a high level what you need to build. You need to build two separate things, really. You need some kind of service that's going to run in the background, that's going to react to messages that are hitting that Kafka topic, do some work when there's messages on the topic. And then you've got some public-facing web application, something that users can use to retrieve the points that they have. And I'm sure you're both familiar with these two different types of applications, right? You've all built similar applications to this. So you decide to start with one of the requirements. Let's not try and do all three things at once. Let's try and do them one at once. So let's start with making it safe. Remember, you're a one-person team working on this project, so you want it to be as safe as possible. And actually, I like to categorize safety into two different types of safety. Application safety, the safety that you have control over as a developer. Handling errors, dealing with edge cases, dealing with panics. All them kind of things that you can have control over. And then there's infrastructure safety, which is the safety of your application that comes from how you choose to run that application. How does the compute you choose, how does the database provider you choose affect the uptime and the resilience of your system? And we start with application safety. And of course, we're at a Rust conference. So we all decide we want to build this with Rust. Really funny story, actually. My girlfriend works in strength and conditioning, so she's got no idea what technology it is at all. Software development, she's got Rust stickers all over her laptop because she thinks Ferris is incredibly cute, so that's a plus for the language, I suppose. And you're already really proficient in Rust. So you go off and you start building this system, and you build these two components of the system. You build the web-facing application, and you build the back-end system that's processing from the Kafka topic. Now, we'll come back to the actual implementation, the actual Rust code a little bit later, but let's actually start with the infrastructure. So I spent most of the early part of my career deploying .NET Framework applications to Windows servers, managing SQL Server databases. It really made me dislike servers. I was at work one day, I finished what I was doing, when we had our desktop PCs, shut down my machine, off I went, left for the day. 10 minutes later, I got a phone call because I'd been remote desktoped into the production server, which meant I just shut down production, which was not a good day. And remember, you're a one-person team, right? So you just want to write your Rust code, you want to ship your Rust code, you don't actually want to worry about managing the infrastructure. Which brings us on to serverless. Have you all heard of serverless and serverless technologies? Is anyone building with serverless technologies? I would say they're building with servers. Okay, some hands, awesome. Now, the premise of serverless is that you can just take application code, ship that application code, and not worry about anything else. Everything else becomes the cloud provider's responsibility. And I actually think it's become a little bit of a lauded term over recent years. It's become kind of co-opted by marketing teams to mean things that it doesn't really mean. And how I like to think about serverless nowadays is not just functions, not just things like Lambda. I like to think of it as a spectrum of choices that you have for how you actually choose to run your application. And this spectrum has two different things at either end of it. From a compute perspective, or from any perspective actually, at the far end, you've got less operational overhead, being as serverless as physically possible, where you take your application code, you ship your application code, the cloud provider worries about the rest. At the other end of the spectrum, you've got that server that's under someone's desk that nobody really wants to touch because it might break everything. And at the other end of that spectrum there, you've got flexibility. You've got the flexibility to do what you want with that compute. If you need a GPU, you can put a GPU in it. So that's the trade-off you're making on this spectrum. Do you want to take on more operational responsibility, meaning you get more flexibility? But there's another interesting dimension in this that often gets forgotten, I think, when we're deciding how to run our applications. And that's the cost dimension. In almost all cases, if you're building with something that is serverless, the line item cost on the bill from your cloud provider will probably be more than running a physical virtual machine when you consider similar hardware requirements, similar allocations, etc. What these things don't take account of is the human cost of actually running and managing servers. It's great if you've got people in your organization who can do that, but not everyone has them skills to be able to run and manage infrastructure. So this is how I like to think about serverless nowadays, this spectrum of choices that you have. And to make that a little bit more specific for a minute, let's look at some actual specific services, at least when it comes to compute. And at the far side of this spectrum, you've got the things that you probably all think of when you think of serverless. Things like Lambda, things like Azure Functions, like Google Cloud Run, like Cloudflare Workers. These are kind of the typical serverless services. But actually, I think when you stop thinking about things serverless being just functions, you give yourself some really interesting opportunities. Services like Azure Container Apps, services like Amazon ECS, like AWS Fargate, services where you can take a container image, you can ship a container image, say, I want this much CPU, I want this much memory, and the cloud provider worries about the infrastructure. So while they might not quite scale to zero automatically like some of the functions as a service do, they still give you that ability to run an application without needing to worry about infrastructure. And then, of course, as you step further down this spectrum, you've got managed Kubernetes, you've got Kubernetes services, you've got actual physical virtual machines that you need to run in the cloud. The far end of this spectrum off the end somewhere is that machine that's under someone's desk in the office. Now, of course, there's reasons why you might need to position yourself at different places on this spectrum. If you need really specific GPUs for something, many of the serverless services won't allow you to have GPUs, so you need to step out and use that different thing. The point I'm trying to make here is to choose the right thing for the workload that you have. And as much as possible, try to stay as far right on this spectrum as possible. Try to think serverless first, because that's going to allow you to take these applications and ship them without needing to worry about infrastructure, without needing to worry about setting lots and lots and lots of things up. So you come back to these two Rust applications that you've got now. You've got these two Rust applications that you want to run somewhere. And you want to run them in as safe a way as possible, at least safe from your perspective as a developer. And for the rest of this talk, we're going to focus mostly on AWS services, assuming that plant-based pizza is an AWS shop. Many of these ideas and things we'll talk about, you can actually apply to the other cloud providers as well. So if you are using other cloud providers, don't worry. That QR code there will take you to a GitHub repo where it's actually the implementation of this application with infrastructure as code in all the different cloud providers. And the first thing you think when you look at this is actually, we don't want to manage virtual machines. We don't want to deal with that. We've had enough of servers. We don't want to run servers. And at this point, you've just got a Rust web application, a Rust backend service. They're containerized. So surely that means you can't use Lambda because you've got a containerized application, right? And, well, Kubernetes, do we want to manage Kubernetes clusters? Probably not. Probably don't need to. Which leaves us with ECS and Fargate. A serverless way of running containers on AWS. You can take your container image, you can ship that. I want this much CPU, I want this much memory, and the cloud provider's going to handle the rest. So you take a Docker image. I'm not going to go through this in detail, but this is an example of how you can do multi-architecture builds for Rust applications in Docker. If you want to dive deeper, a colleague of mine at Datadog wrote a really good blog on exactly how all of this works. I will talk slowly just for a minute while you all take photos of that. There we go, we're getting there. Okay, so you've got this Docker image now, you've got this container image that's packaged up, you want to ship that in some way. And you've got these two Rust applications, you ship them to ECS and Fargate. You've got Neon, which if you're not aware of Neon, this is a really cool Postgres database provider, fully serverless Postgres that will scale up and scale down. It's a really cool service if you're not familiar. And you've got this application running in the cloud now, so you think, fantastic, you can go home, you can put your feet up, you can celebrate because you've just shipped this loyalty point service to production in a week, you've met all the requirements, everyone's happy. Happy days, end of talk. Not so fast. Because Helen comes back to you again and she says, although you've built this application and it sounds like it's safe and it sounds like it's fast, how do you actually know? How can you actually be sure that it is as performant as it should be? So you go off and you run some analysis, you run some metrics. You have a look at, actually, how fast can Rust be when it's running in this serverless way, albeit just containerized Rust applications, right? And as you might expect, this is the top numbers there are the web application, how long it takes to process a web request, and the bottom numbers are how long it takes to process an individual message. That's the P50, the P90, P99, and the max response time. So 300 millisecond response time for an API, not bad. Querying a Postgres database. We all know Rust is fast, right? We all know Rust is performant. I don't need to tell you all that. But now we're getting to the real challenge of the situation, because you might have solved for the speed, the performance, you're using Rust. You might have solved for the safety, because you're using Rust and you're using serverless. You've made the infrastructure responsibility AWS's problem. But remember, this is a non-critical service that needs to be cost-effective and it needs to be sustainable. And what you've got now is two container images that are running 24 hours a day, 7 days a week, even if there are no requests there to be processed, which I don't know about you, doesn't sound particularly sustainable, does it? So what can we do about sustainability? There's plenty of ways, plenty of articles out there, plenty of conference talks, plenty of videos on how to make software faster, how to make software safer. There's not an awful lot on how to make software greener, how to be more efficient with the resources that you're using. So let's come back to this current architecture. Let's come back to this system. You've got your user-facing web application running on Fargate. It's Great for your users, it's performant. Whenever a user comes to retrieve their loyalty points, they're getting a response most of the time in 100 milliseconds, sometimes up to 300 milliseconds. It's good, so you don't really want to touch that. That's good for your users. But you've also got this background service that's processing messages from Kafka. Processing messages from Kafka, even if there are no messages there to be processed, this container is still sat there running, still sat there waiting for messages to come in. Which makes you think, what about these other serverless services? What about these services that are the kind of truest definition of serverless? Services that will scale up and automatically scale down to zero, where you only pay for the compute that you're using. And when you go and actually look at your container images, you can see that you're only using about 6% of the available CPU and about 1% of the available memory. Again, we all know Rust is an efficient and performant language. Which brings us to the truest definition of serverless. Services like Lambda, services where reactivity is their superpower. Services where you only want your code to run when there is work there to be done. And when there is no work there to be done, you want the resources to not be used. You don't want it to cost you anything. And actually, when you think about functions as a service environments like Lambda, they're fundamentally different ways of running applications than you might be familiar with if you're more familiar with running container images. Because instead of having one or a finite number of running instances of your application, where each running instance is handling multiple requests concurrently, Lambda works slightly differently. And some of the other functions as a service providers work in a pretty similar way as well. Instead of having a single running instance of your application, you've got lots and lots and lots and lots and lots of running instances of your application. And each one of these running instances can only handle one request at any one time, a concurrency of one. What that means is that this collection of running instances of your application, all processing one request at a time, they make up your application. Now, of course, you don't need to worry about managing all these things. This is just what's happening under the hood when Lambda's actually working. With these individual environments, you can set the memory allocation as low as 128 megabytes, which you get a proportional allocation of CPU relative to that. So what you've actually got here is lots and lots and lots of running things, running environments, that are all relatively resource constrained, which to me at least sounds a lot like IoT devices or running things on embedded systems. You've got lots and lots and lots of instances of a thing that are relatively resource constrained. Now to me, that sounds like a perfect place to bring back Ferris again. They sound like the perfect partner, right? So to try and work out how we can run Rust on Lambda, how we can leverage these two things together, let's first understand how Lambda works. When a request comes into Lambda, a completely isolated one of these environments is created. So a request comes in, the Lambda service is going to look if there's any existing environments. If there isn't, it's going to spin up a new environment. It's then going to download your application code. It's going to initialize your application code. And that phase of time there is what's known as the initialization phase, or more commonly known as the cold start of a Lambda function. And then once all that's happened, then your code is actually handled. The invoke is actually happened, your request is actually processed. And what this means is that when the first request comes into your Lambda function, that execution environment gets created, that initialization phase happens. But if a second request comes in, whilst that first request is still in process, that whole thing is going to need to happen again. Another initialization, another startup of your application, another cold start. Now, of course, if a third request comes in after that first one is finished processing, then that can be handled by that existing environment. That's what's known as a warm start. And there's three primary ways to invoke a Lambda function. The first is a synchronous invoke. That's where you're going to send a request to Lambda. Lambda's going to process that request, and you're going to sit there and wait for a response to come back. Response comes back, you go on and do your other thing. This is how Lambda would work if you're putting an API in front of a function. You've got asynchronous invokes, which are kind of the same. Something calls Lambda, but says, I don't actually care about the result. I'm going to go off and do something else. Internally, Lambda's going to stack that up in a queue, process through that queue, and invoke your Lambda function. And then the third way this works is what's known as a poll-based invoke. This is where you're going to configure the connection details to your Kafka cluster. Internally, Lambda's going to deploy a fleet of pollers. Then pollers are going to use them credentials, connect to your Kafka cluster, pull the messages off the cluster, invoke your Lambda function. Providing your function completes successfully, it's then going to go back and update the place you're up to in the Kafka cluster. Can't remember the exact term, sorry. So I know what you're probably all thinking now. This need to create a brand new environment every single time a request comes in with a concurrency of 1 probably makes things incredibly slow, doesn't it? So let's go and have a look at the numbers. This is the numbers. So you've now taken that Kafka-based, Rust-based Kafka background processor. You're going to run that on Lambda now. So these are the numbers that I had up earlier for running an application, processing messages from Kafka on Fargate. And if you look at the same numbers for running that on Lambda, the numbers are pretty comparable, which you would expect, right? This is just the time to process an individual message. The big difference here is that you've got about 1/5 of the memory allocated. So from a resource usage perspective, you're using less resources because you've got less resources allocated. But then you might think, well, this doesn't actually include that cold start phase. And actually, this doesn't include the fact that you're going to have lots and lots of these environments running, right? Surely in total, you're going to end up using more resources. So when messages come in to this Lambda function, the average cold start, the average time taken for that initialization to happen was 337 milliseconds, which means the longest time needed to process a message was 337 plus 732, about a second to process a message. And there were 850 invokes, 850 times this Lambda function ran. 3 of them were cold starts. There were 3 initializations. So out of them 850 messages, only 3 of them got anywhere near that 732 milliseconds. Sorry, the second, sorry, with the 2 numbers combined. So what you normally find is, although it feels like it might be a really inefficient way of doing things, actually, because Rust is performing, because things happen quickly, these environments are getting reused over and over and over again, which means actually there isn't actually that much initialization happening. 3 times. Which makes you think, what about the web application? So you might have solved this for this reactive system, this background system where, in most cases, performance isn't actually a big deal. If you've got messages being processed off a queue, in most systems, at least I've ever worked on, if it's 500 milliseconds versus a second, it's okay in a lot of cases. But what about a web application? What about a web application where latency is important? You don't want your users sat there waiting for a response to come back, do you? What would it look like to run a web application on Lambda? So you decide to take the existing application you've got, rebuild that slightly, run that on Lambda, and then you run them performance numbers again. So these are them same numbers again from earlier, them same numbers of running a web application on Fargate with the lowest possible allocation of memory that you can have on Fargate. And these are the same numbers for a Rust-based web application running on Lambda. And again, much in the same way, this is the time taken just to process the HTTP request. So you've got 1/5 of the memory, the performance is about the same. Again, probably not that interesting because we all know Rust is good at doing things when there's not a lot of resources available. And when we look at that initialization phase, this time it took about, on average, 500 milliseconds for an environment to be created, which means the slowest possible response time of this application was 500 milliseconds plus 349 milliseconds, which 800 milliseconds for an API query in a Postgres database, it's not great, but it's not fantastic. And there were 1,350 requests hit this API. The surprising thing about all of this is that 4 of them were cold starts. There were 4 initializations, 4 running environments handled all of these requests. So now you're in a situation where you've got services that are spinning up when there's work to be done, automatically scaling down to 0 when there's no work to be done. They're not costing you anything whilst they're not running. You're being safer, faster, and I would argue a little bit more sustainable. Now, one last thing I just wanted to add is, although doing things like this are cost effective in the sense of things are scaling up and scaling down automatically, most of these services also give you a really generous pricing model. And actually, Lambda gives you 1 million requests per month for free. Forever, I believe. Correct me if I'm wrong. So you can run things on Lambda in a relatively cheap way. Now, I know what you might be thinking now. Hopefully you're thinking, okay, I'm convinced. Where's the Rust code, though? Like, you've just talked to me about serverless. Where's the Rust code? Where's the application code? And that's what I want to hand over to Luciano to talk to you about how to actually build serverless applications with Rust.
Okay. Can you hear me? Perfect, thank you. So thank you, James, for the intro. My name is Luciano. I work as a senior architect for a consulting company called For Theorem. So we help our customers effectively to be successful in the cloud, mostly AWS, mostly serverless. So if all of that stuff sounds interesting to you, please talk to me later. Okay, at this point, we are almost ready to get to see some code, but you are probably wondering, especially if you have used Lambda before. How many people used Lambda before? Great, you're probably wondering, can you even run Rust code in there, right? The answer is, of course, yes, a little bit of spoiler, but I think it's a very legitimate question because if you have seen something like this is the web UI when you try to create a new Lambda, there is one element there that says select a runtime. And if we expand that, basically you can see a list of all the runtimes available. And in this case, you can pretty much associate a runtime to a specific programming language and a version of that programming language. And you start to read there, and the most common ones are probably Python and Node.js. At least these are the ones that I see the most being used by some of our customers. But then you also have other things like Java, .NET, Ruby, and you might be wondering, where is Rust in there, right? And actually, if we squint and we zoom in a lot, we can actually find that there is a little reference there that says, well, you could do a custom runtime that allows you to run either Go, Rust, C++, or something else that you want. So the answer on how can we run Rust on Lambda is basically by using custom runtimes. And that's where the next question comes from, is like, what is even a runtime and what a custom runtime then is, right? So we need to kind of look under the covers and try to understand what a runtime is. And generally speaking, when we think about Lambda, we think about this one unit, right? We write some business logic, there are events, something runs our Lambda, and we get job done that way. But that something is actually one of two components that exist inside a Lambda. So if we try to look a little bit under the covers, we can divide a single Lambda environment in two parts, the runtime and the handler logic. So now one exercise that I want you to do is, James was describing that process of there is an event happening and suddenly a new environment is created inside the cloud in your AWS account. So imagine that you are that one Lambda environment that gets created, and you have some kind of business logic, but you don't know what to do because you don't have an event, right? So the first thing that you need to do is to go off and ask somewhere, what do I need to do? Is there something I can do? And that something is this thing here on the left side called the runtime API, which is effectively an API that from the runtime you can call to literally ask, is there something I can do? Is there something I can do? Is there something I can do? Of course, if there is an environment there that was just spun up, chances are that there is an event ready waiting in a queue that can be immediately returned to you. At that point, an event is just a JSON blob that contains some information that you can use and do something with it. So what you need to do, the job of the runtime at this point is literally just taking that JSON blob, sending it to the handler. So the handler is your business logic. So like, I'm giving you this, please do something useful with it and let me know what is the result. And the result can either be, of course, a successful result or it can be an error. But either ways, it's another JSON blob that we need to take and send it back to the runtime. And of course, the reason why we need to send it back to the runtime is because if you remember, James was describing the synchronous invocation. So for instance, when you have an API gateway, on the other side of the runtime, there might be a connection waiting for a result. There might be a user that just made a request and is waiting for a response. So we let AWS know we finished our job in our Lambda. Please propagate whatever result to whatever is the relative endpoint that that result needs to go to. Now, an interesting thing is that if you actually select the custom runtime on the AWS web interface, it will give you something like this. And I know what you're thinking. Yes, this is Bash. I honestly hate writing Bash, and I don't know why I'm presenting it here. Actually, I know, because I think whoever wrote this was actually brilliant. They managed to make a Bash script really, really easy to follow and well documented. So I think this is actually a really good example of something that explains in a more programmatic way what happens when you are effectively executing that loop in a runtime, in a custom runtime that is, in this case, is written in Bash. So you can also write Bash, by the way, in your Lambdas. So here there are a few distinctive phases. The first one is effectively we are loading the handler code. We actually have two files here. This is the, let's say, the runtime part. The other file is the handler part. So the first thing that we are doing, we are actually loading the business logic from this handler file. The next step, we have this while true, so it's effectively an infinite loop. And this loop is effectively the polling loop. So every time we are trying to see, is there a new event? Let's process it and let's start it over and over again until the Lambda gets shut down for inactivity after a while. In this loop, the first thing that we need to do is we need to go to that runtime API, and you can see that there is an environment variable there that represents the actual endpoint where that runtime API is available. And effectively, there is a REST API that we can call to ask, please give me an event. Is there an event ready for me? Eventually, this is actually a blocking HTTP request, so this request is just going to be pending until there is an event available. Whenever that request unblocks, you have a blob of JSON that you can take and use it to invoke your handler. And when you invoke your handler, of course, you are expecting a response, and then you can take that response, use another API in the runtime API to propagate back the response. So all of that should be relatively easy. So I know what you're thinking. Let's rewrite all of that in Rust. Sounds like a fun challenge. It's like 2 API requests, a little bit of JSON. So how difficult can it be, right? But I'm just kidding, because of course we want to be productive. As James said, we have only a week to deliver a product, so we cannot focus on things like, okay, let's rewrite an entire runtime. But thankfully, AWS has done that, and I like to think that actually they did a much better job than I could do, because there are so many smart engineers there. So we should just take this work and leverage it as much as we can. So at this point, we have, I think, a fair good understanding of the steps that we need to follow to create and then publish our first Lambda function written in Rust. So the first thing is that we need to create a new project. So you could do, I don't know, cargo new, give it a name. Then you need to install dependencies. In this case, we want to use the Lambda runtime provided by AWS, which comes as a crate. So you can just do cargo add the Lambda runtime. Then we need to write the init code. So the init code, again, is everything that happens the first time that your environment, Lambda environment, is created. And in that code, effectively, we want to initialize all the resources that we need to create once and then reuse across multiple invocations. And also, we need to start that polling loop. And there is a function, we will see the code in a second, coming from the runtime library that is literally called run. And we need to call that function and give it our function handler. So at this point, we can write the handler, so the business logic, which generally goes into 3 steps. So there is a part where we deserialize the event and convert it into some struct that we can use. Then we have some kind of business logic, so useful stuff that we need to do. And finally, we have a response that also needs to be serialized so we can send it back to AWS. At this point, the next problem is, of course, we have all this amazing code, we need to build it. And building it comes with its own problems, because you might have, I don't know, all sorts of disparate operative systems and CPUs in your working laptop, but you need to build for a specific version of Linux, which is Amazon Linux. And also you have a choice of only 2 architectures, x86 and ARM64. So of course you need to be a little bit careful that you build a binary that is going to work in the final cloud environment. And when you have that binary that is properly built, you just need to zip it and then call an API on AWS to publish that as a Lambda. So sounds relatively easy, but I will say that's a lot of work, right? So is there an easier way? Because again, we are trying to optimize for speed, not just speed in terms of our program needs to be fast, but also speed of development. So is there another solution that maybe simplifies some of these steps? And thankfully there is, and again, this is another AWS tool that we can leverage. It's called Cargo Lambda. And if you are not familiar with it, this is an extension of Cargo. So once you install it, it basically gives you additional commands that you can use inside Cargo. So you still use Cargo to do most of the things, but now you will have a subcommand called Lambda, so you can do Cargo, Lambda, and a bunch of useful things. What is the first useful thing we can do? Start a new Lambda, so create the scaffolding for a new Lambda project. And because we want to do 2 different things, we want to do a RESTful API, so it will be an HTTP Lambda, and we want to connect with data coming from a Kafka topic. We will be creating those 2 different kinds of Lambda today. So let's start with the HTTP one. So when we run this command, we actually get an interactive prompt that tells us, okay, is this Lambda that you want to create an HTTP function? And of course, in this case it is, so we can just say yes, and the program stops there, but it gives us these 4 files already well organized in a nice structure. So let's try to see what's inside those different files. And let's start with the cargo toml. So this is where we can expect to see all the dependencies that are already made available to us. Of course, there is a name, there is a version and an edition, but the main bit here is dependencies. And the main dependency is this Lambda HTTP, which is actually a slightly higher level version of the Lambda runtime that is more optimized for when you're doing HTTP Lambdas. We will see exactly what it gives us, but it's basically a higher level built on top of the Lambda runtime that I showed you before. And then we also have Tokyo, and the reason being is that the Lambda runtime is built on top of Tokyo, so we will need to have an async main, and that async main needs to use Tokyo. So if we look at the main OS, this is what we generally call the init code. So this is the code that gets executed when our environment is created for the first time. So we import that Lambda HTTP layer, and we also import our handler code that we will see in a second. And then we have this main. This is an async main function. This is basically what starts our program. And what we do here is a few things. The first thing is initializing the tracing crate just for logging. And here we could have a bunch of other things. Like if we wanted to connect to a database, we could establish a connection. If we wanted to create, I don't know, an instance of a secret manager client because maybe we need to read some secrets. This is generally where you will put all the steps that you want to happen once when the environment is created, and then reuse all of these resources across multiple invocations. The final step, what you can see there in line 9, is where effectively we are starting that polling loop. So the run function comes from the Lambda HTTP crate, which is effectively re-exporting the runtime. So the run function that comes from the Lambda runtime. And basically the only thing that we need to do is say, please, every time there is an event, run our Lambda handler. So the function handler that you see there, which is coming from the other file. So in the other file, what we can see here is effectively the pure business logic. So everything that is happening every time that a new request comes into our Lambda. And there are a few interesting bits. So the first one is the signature of this function. You can see that we have an event of type request, and then what we return is a result of a response. And these are two abstractions, this request and response, are two abstractions that will be very similar in any other HTTP framework that you might have used. So effectively a request allows us to do things like, let me check the query string parameters, let me see if there is a body, let me see what's the method, if there is a path, and you can build all sorts of logic, checking all these things and deciding how do you want to process this particular request. Now, this is a very simple example. This is what you get by default from that cargo lambda new. And it's basically doing an hello world in HTTP. So we can get a query string parameter. If there is a name, we are going to store that name. If there isn't a name, we are going to default it to world. And then we create a string called message that says something like hello world or hello whatever name. And then the last part that we need to do is, of course, build a response object to send back that response to the user. And as you can expect, this is just an HTTP response. So we can set the status code. We can set headers, for instance, to specify the content type. And then we can set the body. At that point, we just return that job done. So this is our first Lambda HTTP complete. Now, next question is, how do we test this? Ideally, we want to test this locally before shipping it to the cloud, because shipping it to the cloud, it's always a little bit of an effort. So if we can test it locally, probably we can iterate a little bit quicker. And thankfully, cargo lambda helps us here as well. So there is another command that is called cargo lambda watch. So this starts a local simulator. So this is effectively an environment running in your machine that simulates what happens when you're running a lambda in the cloud. And the coolest thing is that it's actually watching your code. So if you do changes, it's going to recompile your code. So you're always running against basically your latest changes that you have locally. You don't need to commit them. You don't need to push them. You don't need to run a build pipeline. You can change just one line of code, and it's going to be immediately reflected in this local simulator. But this is just running your Lambda. It's not doing anything useful, right? Because again, the Lambda is just waiting for events. So how do we send an event to this particular environment? And of course, there is another command called cargo lambda invoke, which allows you to send events to this local simulator. Now, where do we take the events from? There are a few options here. The first option is that there is an entire set of examples trying to cover all kinds of different integrations that you will generally use Lambda for. And of course, there is an example also for HTTP requests. So if we use that particular example for HTTP requests, we will get a response that is going to look like this. And you might not be too surprised to see JSON, because as we were saying before, Lambda just deals with JSON. So it's always JSON in, JSON out. So they are trying to map HTTP requests and responses to very well-structured JSON objects representing requests and responses. So now the next question is, okay, you might notice here that we have the default behavior, so we don't have a name probably in our example event, because the response that we are getting is just hello world, right? So how can we test that our other case, when we provide a name, is actually working correctly? And in order to do that, we need to see what's inside that particular event, the example one that we are just using here a little bit blindly. And how do we get that particular event? It's actually everything available on GitHub. So if you go on this link here, you can find a list of all the examples that are available. And of course, you can take any one of these examples, download it locally, do some changes, and then just use your local version. And this is what I did here. Sorry, somebody was taking a picture, so I'm going to show it again. There you go. Okay, so what I did, I basically went there, all list of events, downloaded the one that I was interested in, the HTTP one that you see mentioned there. And basically, this is it. Like you can see that I made a copy in a local folder called events, and then I called this particular event with name.json. Now, if we look a little bit closely here, as I was saying, an event is just a JSON blob that tries to model all the different fields that you are interested in an HTTP request. And some of these fields are query string parameters. And actually, there are two versions. There is plain query strings already organized as a map, and then there is the raw query string. And now here we only have an example foo bar. So of course, our application was looking for name. It didn't find name, so it defaulted to the whatever behavior we had as a default. So we can change this and basically turn it into name, Rust Global 2025. And we also need to be careful and update the raw query string as well. And now what we can do, if we go back to our local simulator, we can use this data file flag to use a local file rather than using the remote examples. So at this point, we are basically telling the local simulator, use this JSON that I am providing rather than the default one that you can fetch remotely. And this time, we get the response that we expect, which is basically saying, hello, Rust Global 2025. We are super happy. How do we ship this to production? Of course, Cargo Lambda, our best friend at this point, gives us a command that is called Cargo Lambda build. And there is a very cool thing about this command is that you can give it a flag, the last one you see there, ARM64, and regardless of your choice of operative system or your current architecture in your working machine, is going to figure out the magic to cross-compile your Lambda to the correct architecture. So only this alone to me is a good value proposition to keep using Cargo Lambda rather than just trying to do everything from scratch. A little bit of a spoiler, in some cases it can use Zig, and there are a lot of rant online if you look, why are you using Zig in a Rust project? So you can go and read that in the GitHub repository if you're curious. But there is actually a really nice explanation if you're really curious. Okay, once we do that, effectively we end up with a binary, so this takes some time to compile. I think it took like 27 seconds on my machine. But once it's compiled, of course, this binary is still living in your machine. So how do we send it to AWS? And again, Cargo Lambda is a command for that. So Cargo Lambda deploy will actually package that binary into a zip file and call the correct API on AWS to make that appear as a Lambda function in your cloud account. Now here there is a little bit of an interesting detail that enable function URL. It's an optional flag. You don't have to use it. Actually, I would generally discourage people from using function URL. I don't know if people are aware what function URLs are. Okay, I'm going to give you a super quick explainer. Basically, when you want to expose a Lambda behind an HTTP endpoint, the more production-ready way to do that is to use an API gateway, so an entirely different resource that needs to be configured, and then you can have authentication, you can have logging, you can have mapping of data in and out. It does all the things that you might expect from an API gateway, but of course, it's extra stuff we will need to configure. Here, we just want to test that our Lambda can be called from a URL. So function URLs are kind of a shortcut. It's almost like a debugging tool that will give you a URL that you can just call from your browser or curl or whatever tool you prefer, Postman, and it will just forward an HTTP request, convert it to a JSON, and then send you back the response. So for this case, I think it's fine to use function URLs, but I will say in general, maybe for production, you should make an effort and use API gateway. So doing this little bit of a shortcut here, when we send this command, it's going to take a few seconds. Here, I think it took, like 13 seconds, so it doesn't take too long, and we ended up with a URL. Now, this URL, as you can see, looks a little bit ugly. It's generated by AWS for us, but it's something that we can call straight away and see if our function is working as expected in the cloud. So we can open up a browser, put that URL, and we can see that the response actually comes up as we expect. We can also try to pass a query string parameter, and the response changes accordingly. So congratulations, we have our first Lambda function written in Rust, tested and deployed to the cloud. And now I know what you're wondering. Okay, HTTP, pretty cool, but simple enough. I wasn't expecting anything crazy. It isn't crazy, but how difficult does it get when we want to deal with Kafka? That seems a little bit more like a challenge, right? So let's try to work on a Lambda function that implements the Kafka bit. So taking information from a Kafka topic, we expect in that Kafka topic to find information about users completing a purchase on plant-based pizza, and then we need to look at that data and decide how many points do we assign to the users for every transaction. So what do? We create a new Lambda. And how do we create a new Lambda? At this point, you know the drill, cargo Lambda new. We can give it a name. And we will see again this question. Is this an HTTP function? But this time it's not an HTTP function. So we need to reply no to this question. And in this case, it doesn't stop there. It's actually going to ask us, okay, if it's not an HTTP question, what it is? Like, what do you want to handle? What kind of events are you expecting? And it gives us actually a fairly long list. Here, it's only a section of it. You could scroll. I think there are like 50 elements here. And these are all the most common integrations that Lambda works with in AWS. And one of those is, of course, Kafka. So you can actually type Kafka, and it's going to filter out the search. So it makes your life actually very easy. But then eventually we select this Kafka item here. And again, it creates a file structure for us. So it creates kind of a skeleton for the project that we can start to work with. So we don't need to worry about creating all these files manually, installing dependencies, creating the functions with the right signature, and so on. So let's again have a look at these files and compare them with the previous version. If we start with the cargo toml again, here the dependencies are a little bit different. So the first difference is that we are using this AWS Lambda events crate. And this crate is nothing else than just a big collection of structs using Serdi that are basically useful to deserialize the standard AWS events and serialize the standard AWS responses. So if you look into this crate, it's nothing else than just a collection of structs. And they actually went through the effort of organizing it in feature flags so that you can use, in this case, only the Kafka bit that we're interested in, so that it can compile really, really fast. It doesn't need to worry about all the other 49 structs or more that are available there. Then we have the Lambda runtime. So this time we are actually using the lower level abstraction, and we will see exactly why in a second. And then again, we have Tokyo. Now, the main code is pretty much the same as before. Literally nothing changed. So we are again just initializing, and in the initialization code, we are calling run, which this time comes directly from the Lambda runtime, but is effectively the same function. And we are just saying every time there is an event, run this function for me, please. Now, let's look at the actual handler logic. So this is where the tricky bit is. So the first thing that we can observe is that the signature is a little bit different. So this time we don't have a request and response, but we are going a little bit lower level. And we can see that the abstraction that we have at the lower level is this Lambda event. So Lambda event is just a container object that contains the current context, what is called the execution context of the Lambda. So this is where you will find all the metadata about the current execution, like what's the name of this Lambda, how much time do I have left before it times out. But it also contains your current event. So this is why we have a generic part, because the current event is going to be different depending your integration. Here we are integrating with Kafka. If you are integrating, for instance, with an S3 event, you will have something like Lambda event, S3 event. Hopefully that's clear enough. And then the other interesting bit is that the result is just an empty tuple, because this is an asynchronous invocation. So we are only going to receive events, but nothing is waiting on the other side for a response. So we only need to return whether it was successful or not, but there isn't really an object or a struct that we need to return to a user that is waiting somewhere. So this code is actually quite simple. So the only thing that it's doing is just taking the payload from the event and printing it. I want to do something a little bit more realistic, I guess, just to show you how data is organized in Kafka. So James was already showing before that data is organized in topics, and we generally are going to be listening for one specific topic, so we will receive events that are actually pushed into that one topic, the ordered completed topic. But when you look into a topic, topics are actually organized by partitions, and this is just an efficiency mechanism inside Kafka. So it's almost like you have mini streams inside a big stream, and you can listen to those different streams at the same time. So you can parallelize computing events coming into the stream. So effectively here, what I did, I added a couple of loops, nested loops. The first one to iterate over all the partitions that are available in this event, and the other one iterates over all the records in that partition. And then basically I'm just printing the content of that particular event, which generally needs a little bit of decoding, because when you put events into Kafka, you generally base64 encode them, and then it might be a JSON or a binary, whatever makes sense to you. So here I'm doing all of this decoding and effectively getting out individual events from this big payload that is batching multiple events. So how do we test this code? I went off, downloaded the standard Kafka example from the repo I showed you before, and I changed it a little bit. So here I am assuming that there is 2 partitions. So for this particular event, we are getting events. So this is a batch of Kafka events, if we want. So it's one Lambda event that collects multiple Kafka events together. So you can process many of them with just one invocation. And they are organized by partition. So in the first partition, we only have one event. In the second partition, we have 2 other distinct events. So effectively, we are getting a batch with 3 different events that were put into Kafka at some point. Now, if we print all of this, we can check that once we decode our individual events, it's just a JSON, and we expect to find information that is useful for our task. For instance, the user ID, the order value. Then we can take all of these things, maybe we can group them by user ID, we can sum all the order value, and maybe we can decide, okay, every 100 pounds spent, I'm going to give 1 point to this user. Store it to a database, and then the user can spend those points maybe to get a discount next time, maybe to get some prizes, whatever it makes sense for our loyalty service. So that basically completes kind of the main logic that we wanted to see for Lambda. Of course, you know at this point how to test and deploy this Lambda. It's exactly the same commands. So the next thing that I want to show you, and I'm going to speed up a little bit, is that this is the list of all the events that are the default ones, but you can also have your own custom ones. There are some very specific cases where it might make sense for a Lambda to receive any arbitrary event that makes sense for you and return a response that makes sense to you. Probably the most common case is step functions. Anyone is aware of step functions? Only one person, so I'll give you a super quick definition. So it's effectively an orchestration tool. You can define like a workflow where you have multiple steps, like take data from an API, then do some manipulation, send it to a database. You can do parallel things, you can do loops and that kind of stuff. It's almost like a low-code solution in AWS. But if you want to create your own custom business logic, you can do it with Lambda. And this is the case where you define exactly what is the input and what is the output. And no surprises, here we can just use Serdi. So we can create our own custom request and response, and they need to be serializable and deserializable, and then the runtime does the rest of the magic for us. Now, the last thing you might ask me is,
does that go to another topic? Where does the output go now? Or just
so this you decide. So if you are using step functions, effectively that step will produce an output, and then it's on you to decide visually. You have like a builder, and you can say, take the output and send it somewhere else. Maybe you can have like a chain of multiple lambdas that do multiple processing steps. So this is just to show you a case where you might want to do something entirely custom. You don't want to use the default events and responses. You can totally do that, and it's just as easy as using Serdit. But good question, thank you. Okay, now the last question you might have is like, okay, Cargo Lambda, pretty cool, but it's another CLI tool that I have to use. I already use Terraform, I already use CDK, I already use SAM, I already use whatever. Can I just keep using that? And this is a very legitimate question. I think you should keep using whatever you like. And there are a few reasons for that. I think Cargo Lambda is really, really good at doing a few things. We saw that it's very good at scaffolding a new project. It's really good at local testing. It's really good at compiling, and especially cross-compiling, so making sure it does the right thing for you. You don't have to worry about configuring all of that. But there is a problem. Like, if you need to create a real application generally is not just one Lambda. It's a collection of resources that you deploy in the cloud. You generally have a DynamoDB tables, S3 buckets, you have, I don't know, SQS queues, you can have Kafka, you can have whatever it makes sense for you. And generally, you don't even have only one Lambda. You will have hundreds even of Lambdas in the same project. So you cannot think of doing all this manual deployment for every single Lambda and then figuring out another way to deploy the rest of your infrastructure. So the good news is that you should keep using Cargo Lambda for all of these things, but when it comes to deploying your infrastructure, you should keep using whatever infrastructure as code tool you already love. And the good news is that most of them already integrate with Cargo Lambda, so you can just connect them. So you can connect, for instance, Terraform with Cargo Lambda, or CDK or SAM with Cargo Lambda, and what they will do under the hood is that every time they need to compile, they will be using Cargo Lambda. When they deploy, they already have the binary, and they can deploy your Lambdas together with the rest of the infrastructure. Now, one last thing I want to show you is an actual case study that I did at work. Unfortunately, we don't do nearly as much Rust as I would like to do, but it's happening more and more, and this was one of those cases that I was really happy with, that I could introduce Rust. So this is an authenticator Lambda, and if you're not familiar with it, it's not too complex. It's basically a way to extend the API gateway if you want to do custom authentication. So one example could be something like this. You have a user calling an API. This API requires authentication, so the user is somehow providing a token or some credentials in some way. Then this is like a custom process where we need to validate those credentials in a custom way. So we can tell API gateway, every time you have an authenticator request, send the credentials to this Lambda, and this Lambda has all the business logic to decide whether those credentials are valid or not. And if they are, it's just going to respond, yes, go ahead. And at that point, API gateway is going to forward the request to your backend. Now, we had a project for one of our customers where there was a custom Lambda authorizer that was written in Python. But at some point, everyone was using this API, and this API, the Lambda authorizer specifically, was getting millions of invocations per day. And it was written in Python, so we realized, okay, this is probably one of those places where if we want to do some quick wins in cost optimization, performance optimization, making our compute a little bit greener, we can try to use Rust. And effectively, we re-implemented this in Rust, and it was literally a couple of days worth of work, because the good news is that we Lambdas generally only have to deal with a few hundred lines of code at best. Like, they don't get massive just because you have so many of them. It's almost like nano services. So we could do the changes really quickly, and then we started to measure the results. We put this to production, and we saw 30% less cold starts, 90% decrease in the initialization time, 60% decrease on the execution time, and 70% less memory allocation, which all of that led to 50% cost on this one Lambda alone. Now, to be honest with you, I was expecting much better numbers, because generally when I've seen colleagues doing this kind of work, you can even get to 10x improvement across the board. So I was a little bit confused. I was like, what's going on here? There is something fishy. And I actually started to look at the Python code only to realize that the Python code was actually a wrapper around a Rust function already. So I think if you do this exercise on comparing, for instance, pure Python versus pure Rust, or pure Node.js versus pure Rust, you will see even much better numbers. But anyway, if you're curious, we actually made open source this authorizer. All the code is available on GitHub. And if you go to the repository, you can also have a link to the benchmark, which is in another repository. So you can double check all the numbers and make sure that everything is correct and makes sense to you. Okay, now in summary, what we wanted to share with you today is that we believe that serverless and Rust are a perfect combination together. So if you take the two, put them together, what it gives you is basically great performance, safety, cost reduction, and even environmentally friendly application, which is becoming more and more important these days. Now, the main takeaway for me personally is that if you are looking for an excuse to introduce Rust in your organization, serverless is probably the lowest risk entry point. And the reason being that, as I showed you before, it's generally a few lines of code, literally hundreds or a couple of hundreds. You can probably rewrite that stuff in one day, even using LLMs if you want these days. Ship it. If it works and gives you great result, it's a win. If it didn't work out, you don't have to justify with your boss that you spent months and months rewriting an entire application. So this is why I believe that this is a great way to start using Rust in production today. Of course, if you are on AWS, you can use Cargo Lambda, which is going to make your life even easier because, as you saw, it's just a productivity boost. It does so much stuff for you that it would be silly not to use it. Now, my advice for you is go and build your next serverless application with Rust. And if you need a little bit of help, myself and James are working on this book called Crafting Lambda Functions in Rust. It's still a work in progress, although it's already available in early access. We already published 6 chapters. So if you buy it today, there is a very generous discount. It's like 40% of the final price. And you already have access to the 6 chapters where you're going to learn how to build an entire application from zero to production. It's like a URL shortener, and it uses API Gateway, uses DynamoDB. So you get to learn how to build something that is starting to look like a real application. So check it out and let us know what you think. Being an early access product, of course, everyone is welcome with feedback, and you can help us to shape the future of this book. So thank you very much, and hopefully we have some time for questions.